And they do all this on page 914. They rewrite AT and AN in a few different forms. So again, for the homework, I'm going to let you look that over. I would use this formulation for problems in the homework because, just like the curvature, they had a basic definition and they had another way to write it that was easier for a given R of t. Yes, sir.
Is that in the normal portion? Would that be v squared?
Yeah, you can put kv squared, exactly. I like it. And just to remind you guys, if you're not looking through your textbook, you're insane. So part of my job is to try to explain what the textbook is trying to do. But part of your job is to see if you can figure out how it goes through a proof. That's how you get through math courses. Yes?
I'm not understanding that last part. Multiplying with the normal unit.
So really quick. We got this here.
Yes.
Okay. So we figured out that t prime is like kappa times, and this is the length. Kappa times the velocity, right? The length of the velocity. And t prime, the full vector, not the length of it, but the actual vector, is equal to the normal times the length. Cool. All right. So now using these things, I can now replace this with k times v times n, and there's another v there. So like somebody said, so I can replace this piece with k v n. There's already another v there, so I got k v squared n, and this would be gather. That's the acceleration. And of course this first part, so that'll be the tangential acceleration, and this will be the normal acceleration. So you can just combine those two together and make it squared. Yeah?
Shouldn't that prime marker be outside of the magnitude, or does it not matter?
Yeah, thank you. I was trying to remember that. I think I did it earlier. Okay, cool. Because you first find the magnitude, and then you take the... yes?
The magnitude velocity vector is squared.
Yeah, just because there's going to be two of them. T prime's got one of its own,
Okay.
and there's already one there. Yeah, cool. All right. So that's just the two little things in section 13.4. To get into Kepler's laws of motion, we'll see if you guys have questions on that. Again, these are examples using the tools that we've developed. So part of Calc 3 is developing tools. So we got very basic tools, dot product, cross product, so forth. Then we got concepts that go along with those tools. So this section is sort of a very specific, okay, in the instance of motions of particles, how would these tools be used and what would they mean? Right, so very often we try to do something like this, which is take something and break it down into its components. And we want to make components that make sense. It makes sense to have a component along the direction you're going. That's the tangential. And a perpendicular to that. I like that. Okay. So, 13.4 is really sort of just the application section of the tools that we've developed, hopefully. All right. Chapter 14. Yeah, oh yeah. Chapter 14 to me is the is where we really start to get into it. I mean, so far we've actually just been developing tools and ideas. Oh yeah, what are you talking about, Jeff? The nice thing about chapter 14 is the idea is really kind of, you can see the extension from what we already know. The basic idea of chapter 14 is this. In the past, so we're coming back to function notation. We're kind of leaving vector notation behind for a while. Chapter 14 is functions of several variables. I don't know if you ever noticed, but the official title of the calc books for Calc 1 and 2 is single variable, and now you're in multivariable, so we will be doing like double, triple integration across several variables. Right? So we're used to only doing integral dx, integral dy, but now we can do both, because I want to be able to cover something. Right? I don't want to just be able to go along one line. So we're used to inputs being along an axis, and outputs being above or below that. So all I'm saying is, all that's going to change now, it's not even a change really, is my inputs can now be, for example, we start with this, my inputs could be the xy plane. So let's imagine this room is sitting on the xy plane, right? Somebody carpeted the xy plane. Thank you. Right? All right. I really want this to make sense. So, I can have a function defined according to two independent variables, and this was on that last test, that statement. I want to make sure everybody understood what I meant by that, because we're getting into it. So I can now, instead of having just y equal a function of x, where the output defines how far up or down along the y-axis we move for a given input, I now have, my inputs are going to look like points in the xy plane. So this point will have an output, that point will have an output, possibly many, many points will have an output. We're going to have to talk about the idea of domain. Domains will now look like regions in the xy plane. All right, so let's start with a nice one. Yeah, I love the way you're looking. Let's see, where's a nice one? Yeah, let's do this one. So used to doing something. So notice, this is just like the step you took approximately 5,000 years ago when you first went from saying y equals x squared minus 2 to f of x equals x squared minus 2. F of x took the place of y. So here, f of xy is taking the place of z, 11. So fundamentally, computationally, it's not a huge step from what we've already been doing. Just the letter z is now f of xy. Ooh. Idea-wise, this idea that now if I have a point in the xy plane, then its output is how far up. So if I have this covering over the xy plane, then right here, maybe it's f of x, this point right here is 7, and then maybe here it's 5, and maybe here it's 3, and then maybe it goes back up. Are you guys kind of, and if I go that way, maybe it goes up, and if I go that way, maybe it goes down. Yeah, Jeff, maybe. So anybody hike or like walk? Anybody walk? Move around somehow? Yes. So you could have, and walking through, if you ever been down towards Laurel and First Avenue around there, you guys know that area? Where you have these remarkably, in fact, I mean, you've got that one crazy steep ass thing going down Laurel, you know, you just, oh yeah, if you know what I'm talking about. So obviously, if I'm standing right there, if I go this way, then my rate of change of height will be negative, right? But if I went that way instead, it would be pretty much constant. So I'm going a little bit beyond, that's okay, because I love this idea. The derivative can't be just a single idea, because the derivative will now depend on which direction are you about to go. So if I have this curve, if I have something that's like this, but then this way goes this, correct? Do you guys see what I'm saying? No? Shit. So you can imagine, just like I was saying, if you're standing and there's that deep curve, and if you turn this way, it goes up, and this way and that way is just straight. So what is the derivative at this point? that question makes no sense. You have to say, what's the derivative in the x direction? What's the derivative in the y direction? And so forth. Right? In fact, you have to actually, I have to define what's positive direction, what's negative direction, and so forth. You guys kind of with me here? Yes?
You could even make your own variable that's maybe in between x and y.
Exactly. So anything we do, you can make vectors, or instead of x and y, you can make some other unit vector that's in between them. Coordinate systems are arbitrary. But if you have one that's set and you need to do something in relation to it, we can certainly do that. We know how to make tangential parts. We know how to make normal parts along any arbitrary vector. Oh shit. Believe it or not, we do. All right. So I'm just trying to lay the groundwork for this chapter. So let me see. I got some images to show you here for 14. All right, good. Got to catch up to there. Oh, just keep going with this. I don't know what got me off on the other thing. So on one level, we could certainly just make an XYZ table and go a little crazy. Can somebody help me out with what the domain might be? Now, if you know it, just sit on it for a minute. I want to kind of piece this together. Like, what's the biggest X can be? 2. I like it. Y can X be 2 at the most. And what has to be true about Y then? Y must be 0. And the same thing for X. They're symmetric. I like it. So if you write it like this, what's got to be true about x squared plus y squared? How is it related to 4 again? Less than or equal to. I like it. And of course, that is the equation of circle that's been filled in. Are you with me? So, if this is my origin on my xy plane, then there's a circle in the xy plane above which exists the outputs for this function. Let me let that sink in. So in the olden days, if I had a domain from 1 to 3, that's the domain of my function, then I would expect something up here or down there, something around above or below 1 to 3 existing. And outside of that, I'm not guaranteeing anything. Nothing exists out there as far as my function is concerned. That's outside of its domain. Are you guys with me? So now I'm just extending this in one more dimension, right? So now my inputs, my domain is going to be regions in the xy plane, and above that will be this shape. You can think of it like a tent, whatever gets you through, right? Could be below, oh shit, if it's negative, of course, but, you know, that could just be a little bunker down there. Right? The floor of a bunker below you. Right?
Australian. So if you had this little wavy thing between 1 to 3, if you want to find the domain in 3D, would that just be 1 to 3 on the
well, it depends. It depends on how I define it as I move out. Again, right now I've only defined the domain in terms of x, right? So, and this is the x. What am I trying to say here? So if we call this, this is kind of weird. What I'm saying now is, so the old way used to be, this is my domain. So then if I look up and look down, I should be able to see some outputs sitting up there, or down there, right? So now, this could be my domain. And so above or below this, I should see some outputs. So this could be, you know, the output here. Could look like anything. This one's going to look like what? I mean, who knows what this one's going to look like? You can do it. Put z back in. Square both sides. Add the x and y. X squared plus y squared plus z squared equals 4. That is the equation for a sphere. So it's going to look like the top half of a sphere. Because of this fact, it's not going to let it go below the z-axis, right? Or the xy axis. Xy plane. Right? It's going to be sitting on the xy plane. It can't go, z can't be negative. I like it. All right, that's our first little foray into that. And I just love the ideas that it's a very simple extension of what we've done before. A single input and a single output. Now I've got 2 inputs and a single output. So for every input, there's one output, right? You guys kind of with me? Now, of course, again, before I get any interesting questions, which I love, we first learned about normal functions and then their derivatives, and then there were, oh shit, implicit differentiation, because there are some functions you can't solve for. Why? Well, there are functions, not functions, but relations. There are relations you can't solve for z, but you can do implicit differentiation the same way. So what's going to come up in our future is these ideas of what's called directional derivatives, which is kind of like I was saying earlier. If I go that direction, I'm going to go down, so the derivative in that way is going to be steep negative. If I go that way, it's zero, basically, and if I go that way, it's going to be a little bit positive, because there's a little bit going up. Are you guys? So that's directional derivatives. And then the idea of partial derivatives, which is like treating, if I move along the x direction for a given y, make y constant, and I move only along the x direction. Make x constant, and I move only along the y direction. So those will be partial derivatives. The actual work, the computation, will be easy.
Yes.
Uh,
I know you don't totally believe me, but you've got to remember your derivatives for one thing. Yes?
What's the difference between a partial derivative and partial derivative is over, it's like a function of over the entire y.
Yeah, exactly, because yeah. Directional derivative is much more specific, and it can be along some arbitrary direction. I like it. So they are intimately related, but not the same. I like it.
If you want a directional derivative, like 45 degrees in between.
You can do it.
And y.
You can do it, but that's way in our future. We're not even to the point where we can do a directional derivative, period. I just talked about them quickly. Okay. Oh, one last thing here before I let you out here. This is kind of cool. Let me see if I can do this quickly. So if you haven't signed up for Wolfram Alpha yet, it's fine. You don't have to. But it would make your life much easier. Let me show you one thing, and then we'll head out. Actually, maybe let me show you two things, and then we'll... Yeah, whatever, Jeff. Do whatever you want to. All right. I will. Anybody use Apple Maps? Do they still have an Apple Maps? I'm just asking. I don't use it. I don't use any Apple anything. But I'm just wasting time on it. It's going to show me what I want, sort of.
Is that what the LCDs with topological?
Yeah, this is one way to do it, yeah. Is it showing up there yet? They used to do what I really, really want. I guess if I put it on PC, you guys can see it. Okay. So Google Maps, of course, what is this map of? Besides Helix, I mean, what kind of map is this? Yeah, topographical. And on a truly topographical map, you could see these, what should be very familiar to us. In fact, I hadn't looked at Google Maps in a long time for their terrain, and they used to have what I want. What's missing from this, of course I have Google as my home everywhere. All right.
Are you looking for an elevation map?
There we go. This is a horrible one. All right. I didn't mean any offense against it, but
How about the ones that go left to right?
here we go. Oh, if only it was bigger. All right, that's horrible. Oh no, that'll be all right. So, I mean, this is an attempt. We've done this before. We've actually physically done this before, where we take an image, a 3D shape, and we draw traces in the XY plane, for example. Right? We can do it in any plane we want to, but for right now, we're going to pretend like XYs are only inputs. Later, we're going to say, oh yeah, it could be the ZY plane or something else, and get all freaky. but just to start off with. So these are all these traces, and this is what's called a contour map, which kind of makes sense. It gives me an idea of 3D characteristics in a 2D setting, so it's a little bit easier to look at. What do you think is meant that these lines are so close together while these lines are further apart?
Steeper.
I like it. So that actually, calculus terminology would probably be
Faster rate of change.
beautiful. Faster rate of change of height. I love it. And that would just be like the derivative of z in that direction. Does that sort of make sense? I mean, right now this is an overview of the entire chapter in a sense, right? Directional derivatives are in our future. What I just said makes physical sense. The closer these lines are together, the faster the height of that ground is changing. So that makes sense. So somehow, computationally, that should work out the same way. If I walked along this line, what would be true about my walk? Would it be a strenuous walk? If I picked a line and just walked along that line, does that make sense? Like I pick this line,
No.
somebody drops me off in a helicopter, and I walk along this line. Because every line is defined to be a specific height. I love it. So I've just taken a height off of my shape and put it into the XY plane. Another series of heights off my shape and put it into my XY plane. And we've done that before. We're just doing it a little more focused now. Our XY plane is our inputs. And these are my outputs for those inputs. It's just easier to kind of handle when I put it like this. So if you use Wolfram Alpha, which I'll show you next time, it actually shows you contour maps also. I just never pointed them out before. Every shape I've done in Wolfram Alpha, I could have scrolled down a little bit, and there would have been a contour map. And they actually do theirs colors. The lighter the color that's coming up out of the page, the darker it's going down into the page. So it shows you like this would be light, and maybe there'd be a sinkhole over here if I was in Florida or something. I used to live in Florida, so that's the only change. Oh, look, it went down. It would be darker, you with me? So lighter, darker. Cool? A little bit? Okay. Sorry, I was talking over here.
Basically just taking a 3D object and flattening it.
Exactly. Yeah, we've done that kind of thing before. Just the outer rim of it, right? I like it. That's enough. That's plenty.
Are you doing all the stars today?
Yes.
Mostly just the substitutions. I got 5 until then.